Come on and party.
Okay, let's get started. I'm pretty excited because I've been thinking about doing this kind of thing for quite a while now and planning it. And to actually be doing it feels kind of special. I have no plan. I don't know what to do first. But we might just go through a short demo of what this is and what it can do. So I'll go ahead and run it. If anyone has any questions, let me know. And then we'll program a little bit, maybe fix a couple of bugs, because there are lots of them. So this project is a 16-bit real mode operating system for x86 processors and computers based on those. So that would be the computer that I'm running on now, all the way back to the first IBM PC machine, the 5150. That was the full model number of it. I don't have anything nearly that old. The oldest piece of hardware I have is a Pentium 100. I ran this on that months ago, a much earlier version. One of the emulators I use is called Virtual XT, and that is emulating that class of hardware. I'm targeting that. we can run the operating system. I use QEMU and Box, BOCHS. I use those more than anything for development. We can run it in those. So this is QEMU. Here's a bigger view of that. So this is the console here, which is part of the shell. So there's one program that can run on startup, and everything goes from there. So the way I deal with running multiple programs right now is to do different images, build different disk images with a startup program embedded in there. So if I want to run the tests, I build an image for that. If I want to run the fourth language, which we'll probably get into later, build a separate image for that. If I want to run the shell, which is what we're looking at right now, I build an image for that. So we're looking at the shell, so this is pretty basic. You can type commands, and all commands are programs. So this is where you would run any program. So one thing we can do is get a list of all the files that are on the system. Do that by typing ls, press enter, and we get a list of files. That's everything. So that's all the programs, all the test data, and so on. Everything that's on the disk, the virtual disk image that gets emulated. So some of these files we can run, some of them just have stuff in them. If we type cat or concatenate, we can display the contents of a file, view it. So there's a fourth program to list. That's the fourth version of list. That's not what we're running, but that's what this file is, ls.fth. If I type cat ls.fth, press enter, it'll show the contents of that file. Just a couple of lines. They're much bigger files. Hopefully this works. There's a larger fourth program. So that's what we list. There's a bunch of other programs. Hello. Just says hello. And let's see what else we have. Time. I'm not even sure if this one works. Okay, it runs continuously. That shows the system uptime. That's like a test program to do that. So this is actually a multitasking operating system, meaning it can run more than one program or manage more than one running program at the same time. That kind of works. Things got much more difficult when I started trying to add multitasking support. But it sort of works, and we can look at what we have here. So I'm going to press Alt and N, and you can see up at the top that this is console 0. If I press Alt N, I go to console 1. So I can now do stuff in console 1. I can run programs. If I press Alt N again, I go back to console 0, and that program resumes. So we can have multiple programs running at the same time. How that actually works is the kernel, which is the kind of the core part of the operating system, switches back and forth between them really quickly. So after some small amount of time, like some number of milliseconds, it switches from the currently running program to whatever program is in the list of running programs that's eligible to be restarted. And it halts the one that's running currently. So multitasking means stopping the thing that's currently running, going to the next thing and starting it, and doing that over and over again. If anyone has any questions, let me know. If you'd like me to explain anything, let me know. I'm just going to explain a few things that I think are probably the most interesting. So if we let this keep running, it'll keep running until it exceeds the size of a 32-bit integer, which is the size of the integer that holds the time that the system's been running. Anyway, if we press Alt-N, we should go back to our other console. Yep. Alt-N again goes back to the first one. Most of the resources that you can get to as the user of the OS are exposed as files. So the virtual floppy disk is FDO, so ls/FDO. That gives us all the files on that virtual floppy disk. Here's a virtual file system that exposes the process system, or at least some of it. So we can look at what all the running processes are by typing ls/proc. So we see 0, 1, 2, 3, 4, 5. Those are the process IDs. Those are the things that we currently have running right now. And we can get more details about each process by doing this proc/process number /status. So it gives us the name of the process, its status, and the memory segment that it's running in. So if we do that again for a different process, this one's different. So the first one was the kernel. That's always process 0. It's the first thing that starts when the machine starts. And then process 1's the shell. We call that PID1. So that's the single process that the kernel starts. Then the shell's responsible for managing any other processes that are going to start. And that's in memory segment 2, or 2000. So each program can occupy a single physical segment of memory. And on this CPU, 8088 or 8086, which all the current x86 CPUs that are in most consumer PCs, what they call PCs today. The 8086 and 8088 were the first of that line. So a segment size for that CPU architecture is 64K. 65,536 bytes. So that's what this segment address signifies. It's the second segment. So second 65,000 blah blah bytes in the system. The shell's the third. So each process has a dedicated 64K segment of memory that it can occupy. We can look at these others. So the console program is something the shell starts. You're probably going to see crashes, lots of them, by the way. So that's all our processes. So the shell starts the two consoles. So we were switching back and forth. See? First console. Second console. First, second. Those are the two consoles. Did 2 and 3. By PID, I mean process ID. Then the fourth process is the time program. That's the program running in the other console right now. And then the fifth process is the cat program. That's the program that's actually running to print what is in this process status file. So that's processes. And again, they all have 1, 2, 3, 4, 5, 6. These are the physical segments that they start at. So each one gets 65,000 blah blah bytes of memory to work with. That's almost it for interesting test programs. There is other stuff we can do. There are file management capabilities on the disk, so we have this, press LS here, we see our list of files again. If we type, let's look at this test all.fth. Oh, I can't type an underscore because I haven't added that to the keyboard program yet. Okay, good to know. I'm gonna like over here take a note of that. Alright, so somebody's got to add that underscore to the keyboard program. What's another one? So, yeah, okay. ls fourth of that fourth program. We don't care about this, so we can just delete it. And it doesn't work, so the RM program must not be installed. But the kernel will create, delete, open, close, read, write files onto the disk. And the disk in this case is a floppy drive, because we're using an emulator. It's a virtual floppy disk, 720 kilobytes. That's the size of the disk drives, the capacity of the disk drives that were on those early IBM PC computers like the XT. So that's it for the first demo. There are a couple other demos that we can look at. In fact, let's go ahead and run one of them. These are the automated tests. So I have a test suite of automated tests that run to verify that the system is doing what I think it should be doing. Important because I change a lot of things and then everything breaks. Tests help things to break less when I change a lot of things. Now, you saw everything scroll there. There's no kind of scroll back functionality yet, so I can't like scroll up in the screen here and see what scrolled by. But that doesn't matter because let's close the emulator. We're done now, so we're going to go to the text editor. This is a log file that's written, so there's a serial port, virtual serial port, that the emulator can write text to. So the operating system writes its output to the serial port. On a real computer, that would come out the real serial port. So if you had a cable connected to that, you could connect that cable somewhere else and get the data out of it. With the emulators, it's a virtual serial port, so that data goes to a file. So that's how I can look at the results of the test. The output's here. Actually, let's put this just on a bigger window for the time being. Here's the output. So all the test output, and it tells us how many failures do we have. So if I add a bug, hopefully test cases will catch that. They don't always, and I'm working on that. I'm working on better ways to test against regressions. Because what happens is things will be stable for a while, and then I'll change things, and then everything will break. Then I'll fix a bunch of bugs. Everything will be stable for a while. Then I'll add something new. Everything breaks. So a better test suite would stop against that, because then I can run tests as I'm making changes. And when I do something stupid, tests should catch that. So we can look at all the tests. They're all categorized. So formatted printing, which is converting things to something you see on screen, like converting internal representations of data, like integers, bits and bytes, like converting those things to things that you look at on the screen and see and recognize as a number. And that's formatting. Strings, so sequences of characters. There's a lot of code to deal with that. And for anybody that doesn't know what a string is, that's essentially a list of characters. So what I've got highlighted there, I mean anything on this screen. The way it's represented in memory is you have a byte or multiple bytes that each represent a letter, and you just have this connected together. And that whole thing, that sequence of letters, that's a string. So we've got string tests, file tests for opening and closing files, listing directories and stuff. I/O tests, input and output. Reading, so that's reading and writing files, essentially. Disassembler, these are programmers' tools. Memory testing. So allocation, memory allocation. That's for heap dynamic memory allocation, which we'll get into. Tests for data structures, buffers and vectors. These are structures of data that make our lives easier as OS programmers. C language standard library, which we don't really support. It's not that important. Virtual file system. Process management, which is what we were talking about earlier. Starting and stopping programs, things like that. Managing the list of running programs. Managing and switching between programs that are currently running. Disk drive tests, so reading and writing from the floppy disk. FAT is file allocation table. That's our file system. File allocation table, FAT file system was first seen, I believe, in DOS, MS-DOS. And that's what we use for our file system here. Where were we? System calls. So a system call is how user code accesses resources provided by the operating system. So that's something like opening a file would be a system call. Closing a file would be the system call. if you're writing a program for this operating system, you're not allowed to directly open a file. You call the kernel to do that. The kernel opens the file for you and gives you an ID, and then you can manage the file using that ID. So the kernel does that on your behalf. And that's essentially what an operating system does, is manage the computer's resources on behalf of a programmer that's using it. Okay, so yeah, processing processes, so forking, which is how you create new processes. Changing the program that a process uses. Running processes, exiting processes. Those are all things that we test. And then we also test the program that runs the tests. When we get failures, we get reports like this, the expected and actual values of the things that we were supposed to see and didn't actually see. These are actual intentional failures. These are supposed to be like this. So I don't know what to do next. So I'll just make something up and ramble. We're going to look at the list of files that's in the project. Let's not look at it all at once like this, I guess. We'll look at the first level here. This directory structure gets pretty deep. So this is the code. This is all the files that are in here. It's broken up into sub-projects, smaller projects. So boot is the bootloader. It's a small program that runs when you first start the computer. And that's what kind of prepares the machine's environment to start the operating system kernel. And the bootloader transfers control over to the kernel. And the kernel kind of gets the operating system ready and then starts running code. So those things are kind of at the heart and core of the operating system, with everything else supporting it. Everything else is user code. So there's this distinction between kernel code and user code. And kernel code is the operating system code. It's what manages the resources of the computer, being like files and memory, being the main resources we're talking about right now. And then user code is anything else. And the distinction being that user code calls kernel code for those things to happen. So you want to open a file. The user code calls the kernel. The kernel gives the file back. You want some memory. Well, it's dedicated, so actually this kernel doesn't manage that. So you bother the kernel whenever you need files open and closed, or the system time, things like that. So all this stuff is user code, but it is part of some of it is part of the operating system. System has a lot of things that help the programmer talk to the kernel. So a lot of, well, we'll get into it. I'm not sure how to explain it because system is pretty big. It encompasses quite a few different types of projects. And then automated tests, which we looked at. Tools are things that kind of mainly used to prepare the disk images. And then user code are all the programs, like the file listing program, the hello program, the gap program that we looked at earlier. That's all user programs, anything that's meant to be run from that shell that we were looking at. So digging down into any of these directories, you see a lot of files, and what we're really interested in probably is the C and the H, the C and assembly language files. So if you look in the kernel, you see all the stuff that the kernel does. Interrupts, which we'll get into. Initialization, keyboard, pipes, which are ways that programs can talk to each other and talk to the kernel, process management, testing, and the virtual file system. System has a ton of stuff. And this is all memory management, CGA graphics, disassembly, and disk drive interface, device management, the file system, user interface, tons of stuff. There's quite a bit of code in the system library. And one of the challenges is figuring out where stuff belongs, organizing everything and figuring out where it goes. So we can look at some code just to get an overview. I mentioned the bootloader, so the operating system actually starts here. There's this kind of setup stuff describing the layout of the floppy drive. Then after that, we initialize all the registers of the CPU and get the stack ready. The stack being the area of memory, the first place that most functions in a program are going to put a lot of the data that they're using on the stack. So here we're initializing the floppy drive, resetting the floppy drive. And we use the system BIOS, which provides low-level functions for reading and writing for the floppy drive to do a lot of this. So after that, we load the sectors from the floppy drive that contain the kernel image. And we have to handle any errors that happens, because floppy drives can be unreliable. So if errors happen, then we retry a couple of times, and then we give up if that ultimately doesn't work. And there's some code in here that shows messages, error messages, and things like that. Status messages, because a bootloader is kind of hard to debug. It's kind of hard to figure out what may be going wrong with it. After the kernel is loaded into memory, then we start it. Jump far, 0 into the kernel's code segment. And then the kernel starts. And the rest of this is supporting code, so it's routines that do a lot of the stuff that I mentioned earlier, like error numbers, converting memory to things that can be displayed on the screen, stuff like that. The bootloader can only be 512 bytes. That's the architecture of the x86. So the way to have a code that's more than 512 bytes is just to load it in the bootloader and then go somewhere else. And that's exactly what we do. But it means that this program has to be pretty small. So I said we're in the bootloader, then transfer over to the kernel. That's this. Now we go to this main function that initializes a lot of the different parts of the system. We have to initialize a serial port. We try to do that pretty early so we can do the logging that I mentioned. Write logs to the files to see if something went wrong. Then we do some really fundamental initialization of all the devices. Devices being the serial port and the keyboard. Hi, Mistress. Welcome in, how are you doing? We're doing the first operating system development stream. Rocket Sun redeemed this a few weeks ago now. Okay, so we do this initialization of devices, then initialize a scheduler, which switches between processes, like it mentioned. Then the virtual file system. So when that's done, we start installing interrupt handlers, which is something we can get into if anyone would like. But they essentially capture the events that are generated from a system call when user code calls a kernel, or when hardware needs attention. So like when you press a key on a keyboard, that's going to generate an interrupt. And we have to install handler code that will do something in response to that event. So that's what an interrupt handler is. So there's a few of those. Lots of this kind of initialization stuff, interrupt handling stuff. So then at the end of the kernel startup routine, that's when we execute some user code. So once the OS is ready, it needs something to do. And it starts what we call PID1, process 1. And that can be anything. So when I ran the tests, that's a process 1. When I ran the shell, we can type commands, that's another process 1. It's just whatever the kernel will run once the OS is ready. And the main point there being giving you some interface to use the operating system. So that's what this does. It executes that, then the kernel sleeps forever here while true. So this initialization code ends and the kernel just does nothing, but it's not totally true because it will still get and respond to interrupts. What else can we do? I don't know. We can look at some diagrams. Because I've been making some of those lately. We can possibly go in and fix some bugs, because I've been making a lot of those too lately. Yeah, let's look at some diagrams. So I've started to do these so I can keep inside my head how everything works. That's been one of the challenges here, is making changes and keeping track of all the changes. I've made tons of mistakes. Way too many to count, although I should have made an effort to count them all, so I don't make them again. I've counted some of them. But one of the things that happens is stuff will get too complicated. I'll try something, I'll forget what I did, or I'll try a couple of things and they won't work well together, and that kind of thing. Or I'll forget how something works and I'll change it, change something and not account for how some of the thing is working. So what I've tried to do is start to get more organized around that. Making diagrams is one way that's helpful there. So we can just take a look. Okay, so these are some of the system call operations. We can actually look at all of them. They're all defined here. System call numbers. So again, a system call is any kind of request that user programs make to the operating system kernel. And they all have some purpose that they serve. And we'll quickly go through some of them. So fork and exec are how you create new programs. Start new programs, I guess I should say. So if you're the shell and somebody types ls to get the list of files, then the shell program forks, makes a new process, and then execs to run that ls program in that process. Exit, that's how a program says that it's finished. So the kernel knows to close it. The file functions perform operations on files, so open, read, write, create, close, delete files. Files just being what you think of normally as files, stuff that has stuff in it. Stuff that has stuff in it, yep. Wait. A process can sleep. Or I'm sorry, no, wait. So a process can wait for another process to finish. Let's wait. Pipe. Makes a pipe. And a pipe is a special file that two programs can use to send data between themselves, between each other. Sleep. Makes a process sleep. So if you want to if you want to not do anything for a while, but not use too much resources on the system. So say you're a program and you're waiting for something to happen, but you can't do anything until that thing happens. Well, you can sleep, and then the kernel knows to not run you for a while. So it makes it easier on everything else in the system. And time gives you system uptime. I'm skipping some of these because they're either not finished or not that interesting, I think, right now for like a start. But ask any questions or answer any questions if anyone has any. Time gives you the uptime, so then the amount of time that's passed since the system has started. This is chill Linux, kind of. It's sort of like a chill DOS / Linux. It's kind of a cross between those two things. We're just looking at the code though, so I don't know how long you've been here, Mishras. I did a demo. I'll go back and we'll go through that demo again quickly, like another round of that. Shell that. Okay, so the middle window here in the center is the emulator window. QEMU, so think of it as a CRT running it on an old computer. So the console's up and then we can type commands. So that means the kernel is started and it started the shell program. Shell program waits for the user to tell it something to do. So there's a few programs we can run. You can type ls. That gives you a list of files and their sizes. And there's a few test programs that you type hello. You get a response back. It says hello to you. We can type cat to look at the contents of a file. So on that list, we've got ls.fth. We can type cat ls.fth. It tells us what's in that file. Well, OS run Tetris, if it's in x86 assembly, then probably Metal Machine. With a small amount of work. If it's in C, then maybe, but it depends on how it uses the hardware resources of the machine. If it's making bias calls and stuff like that, then some porting might be necessary. I haven't run too many programs from DOS or that era on this yet. There's no support for exe files or COM files. The executable file format is called MKZ, and that's an extremely simple file format that contains some information on the on like the memory allocation and stuff like that that the thing expects, but it's not as complex as exe is. I toyed with adding exe support when I finished the first milestone, I guess, of this, but decided to do multitasking instead. And it was not long before I regretted that and wished I'd added exe file support. Yeah, right into the bare metal is a better idea for sure. There's still, we still use a lot of bias code, but that causes problems because the bias isn't reentrant. So calling it from an interrupt and then calling the bias again causes some issues. So it hasn't become top priority yet, but I've got to convert some of the calls, like the floppy drive read and write code, away from BIOS to something else. And the first I did was for the graphics, like a startup BIOS for everything, and managing the display, like CGA. The BIOS caused a lot of problems fairly early on, so that was the first thing I scrapped, started over. Yeah, multitasking made it much more difficult. Far, far more difficult. If I were to do this again, if I were to start over again, I made tons of mistakes. But now I know. If I were to start again, then I wouldn't... If I knew I were going to do multitasking, I probably would not have started targeting real mode. I probably would have started with something that ran in protected mode to get the benefits of memory protection. And then either like in parallel or after that ported what I could over to real mode instead. Because multitasking in real mode, and it's all the worst parts of concurrent and parallel programming without the benefits of memory protection. So it's been difficult to figure out how to do it. But I'm learning. I did actually start a protected mode version to run on 386s and higher. So I don't know, I may do more of that. Again, just for like the memory protection benefits. Make development a little easier. So anyway, yeah, this is the shell. We can see limited support for multitasking here. So if we type loop, all this does is run stuff in a loop. This loop just increments values and prints them. So if I press Alt-N, that goes to the next console, console number 1, and I can run another program here while the other program's still running. Then I press Alt-N again, I can go back to that other program. And presumably I can keep doing this and everything will run, nothing will crash. And if we ls/proc, it tells us all about the processes that are currently running. And if we cat proc ID status, it tells us about the process. So we get process ID, name, current status, which is running, and the memory segment, which is 1000 hex. If we do that for the rest of the processes, then we can see what they're all doing. And the other program should still be running, yep. Okay, switching back. So the kernel is always PID 0, process ID 0. The first user program to launch is always PID 1, so that's the shell. The shell launches 2 support programs, 2 different copies of the support program console to manage each of the consoles that we're using. We're using 2 right now. Then loop is what we started in the other console that just prints a series of numbers. And then cat is the program that we run to actually view the process status. So that's everything that's going on right now. And then each of the memory segments. So every running program gets a dedicated 64K segment of physical memory that it occupies. The kernel being no exception. It gets the first, not the 0th, but the first segment. And the PID1 gets the second, and so on, up to the process limit, which is 8 right now. I believe 8 is the maximum number of processes that can be running. So is our loop program still running? Yeah. Neat. So that's basic usage of the shell. There's another shell, which is Forth, the programming language, a Forth interpreter, which I've been working on. We'll look at that a little bit, but that is that's become a distraction because it ended up being larger than I thought. So I'm not putting as much time into that right now as I am into trying to make things stable. All right, so that's a demo. We'll do the Forth demo in a little bit here. So I'm going to close that. So we were talking about the system calls. Again, a system call being basically anything that user code, a program you run as the user, does to request something from the kernel. And these are some diagrams of how those things work. High level, without a ton of detail. So open and close, so like if we want to this might not be the best example because it's not showing the user end of this. Hang on. Fork and exec are harder to explain and probably make less sense to anyone that's not familiar with the concepts, so let's look at files. So this is a sequence diagram showing how the open system call works. So pretend there's another box that says user on the left here. That's something I should have added. But user code calls a function. And well, actually, we can look at it. There are C language functions for all the system calls. So if you were a user program and you want to open a file, you call msysfile open. And you ask it for file ID and you give it file name on the system. So then you call this function and that goes to the kernel through an interrupt. And then the kernel manages that request by going through a bunch of internal layers to prepare that thing for you and then send it back. So the kernel will, well, what did I do? I clicked the wrong way there. Okay, so the kernel will internally allocate a file for you and initialize it. And it'll go to the file system driver, whatever that happens to be. So if it's a physical file on the system, like something that contains data, then that's FAT12. That's our file system driver. So FAT12 driver will then go to the floppy drive and load the appropriate sectors needed for that. If all's well, that comes back and says, okay, good, file's ready. So then a file gets added to the list of files for the process. And yeah, the IO system. So the actual, like, the ID that comes back here in this call. That's initialized. And when all that's done, then kernel says, okay, here's your file ID, and then you can manage it. Close is similar. So if you're user code, you type file msys file close, you make this call with the ID of the file that you opened previously. Then the kernel starts going through its layers. Find the open file, close it, which basically means like remove it from its list of files and processes and stuff like that. Make sure we're not going to accidentally write any data to it anymore. Free all the memory and other resources that are associated with having that file open, and then send an OK back to the user. So that's what a system call does. The user, okay, why do you need a system call? Because this is a multitasking operating system, so if you have two programs that both want to open the same file at the same time, those programs are running at the same time, so very quickly swapping back and forth between the two running programs. Call them program 1 and program 2. If program 1 and program 2 both decide to open that file at the same time and start writing to it, then you can have a problem. So that's why the kernel manages that resource, because it's not really a shared resource. There's restrictions around who can do what with it at one time. So that's why you need a system call. That's why you need a kernel. Because if every program's just doing whatever it wants, it doesn't know about the others. And bad things can happen. So that's the whole point of having the system calls, and this is what happens when we use them. There's other reasons too, but that's one of them. We'll look at like one more system call, and then I'll move on to something else probably. Okay, well, let's look at exec. Exec is how you create a new program. So when you use a code, you know what you want to run. So for that shell program, somebody types ls to get a file list. The user knows that that program's called ls. So that's what this system call is for. msys exec. And you give it the file name and the arguments to the program. And so you call msys exec, and through the system library, you call the kernel. The kernel gets that information, and through its internal layers, virtual file system and process system, it gets that file open. So it reads all the data from the disk drive, loads that into memory for a process, allocates a process, starts a process, and then sends that result back to the user. And a lot of this stuff can fail for any number of reasons. So one of the important parts of all this is to report errors back when they do happen. So if the file is not found, if the file doesn't exist on the disk, so say Somebody types LST instead of LS. That's a typo. So then LST comes in here, and this process will start to go. The kernel will try to open a file called LST. The file system driver, the FAT12 driver, will not be able to find that file. And they'll say, no, I can't do it. So at that point, the error will come back. And then we don't do all this other stuff to start a process. We just send that error back to the user. Same thing if an error that you would expect, totally expect to happen happens. So say that the user started too many processes. You can have 8, I think. So the user tried to start a 9th process. It doesn't work. So then the proc system, when it gets to that point, is going to try to allocate a new process and says, hey, don't have any other processes. You started too many. So then we send an error, and that propagates back through the kernel to the user code. They get the error, process file limit reached. And they get to deal with it. So that's kind of how the system calls work. I don't know what to do yet. We could talk about interrupts. I could do the 4th demo. That'll be pretty fast because it can't do too much. But let me think about it. I'll take a quick break. And anybody in chat, if there's any questions that you have or is anything you want to see, let me know. I'll do it when I get back. I'll be back like 3 minutes or so. Where's my BRB thing? I need it. All right, BRB. I'm gonna, I think, work a little bit on a bug I was fixing earlier. And I'll talk about what I'm doing. Feel free to interrupt with any questions or whatever. Or just a chat if you want. I actually have a lot going on right now, so I added a new testing methodology. It's kind of like somewhere in between what you might call fuzz testing and property-based testing. But I've had, I don't know, recently it's actually been pretty good as we've got new techniques. But I've had, once I started working on multitasking, started getting a lot of memory errors that were really hard to track down. Because once you have two programs running at a time, that makes things exponentially harder, 10 times harder. So I've been looking for ways to test stuff like this. And this new fuzz property testing has been pretty impressive so far. It's actually helped me on a number of bugs. It takes a lot of time to write the tests, but probably worth it in the long run. There's other things I found too, better ways to program, ways to program safer, more safely, keep track of bugs and things like that. How long? About a year now, amazingly. Amazing because it's the first time I've ever done anything, stuck to anything for this long. This and Twitch are probably the first two projects I've ever done, personal projects that I've spent a year on. I think I probably started around April of last year, but it was about June that I started to get pretty serious with it. It's hard to stick to projects. Sometimes you got that right. For me, it's almost impossible, but it seems to be getting better lately. Yeah, that sounds awesome, Metal Machine. Is that hard with the whole new job and everything? Has it been hard to make progress on it? Yeah, that's one thing that can get pretty hard, especially if you do software development in the daytime anyway. It can be hard to do it later in the evening. And do it more. Yeah, that's true. Any relationship, long distance being no exception probably, although I don't think I've ever personally done that for a very long time. But certainly friends and family commitments reduce the time, but that's a trade-off, right? All right, so when I added these new tabs, I started finding bugs all at once. I get into this Russian doll thing sometimes where I start finding this one bug, and then as I investigate that, 3 other things break and I have no idea what's going on. So in this one, the heap allocator, the dynamic memory allocator, does not check to make sure that the base of the heap is lower than the top of the heap. And so what that means is that if the requested allocation size for the heap is greater than the available amount of memory, then we do not work correctly. So I should have gotten this right the first time. I added this bug, but that's not how it happened. So I think I fixed this already. Now I check that. We check and make sure that we haven't requested more than is actually available. So I think we're good now. I'm not going to commit it, but we're good. We can actually look at this code. Why not? Look at the purpose and use of this code. So, oh, YouTube wants to make sure we still want to listen to music. So anytime we start a program, we initialize what we call the heap. And the kernel does one, I believe. Okay, not directly, but when it uses dynamic memory, then the heap is allocated. These test codes. So if I open up the code for one of the automated tests, one of the first things that happens is it initializes the dynamic memory. So what is that? Let me, we're going to do some funny diagrams. So dynamic memory heap. Here, let me turn off this. Here, we'll turn down the autocomplete interval so it doesn't pop up with so much stuff. Okay, so if you're running program, you want to use memory, and memory generally looks, think of it looking like this, basically. Like a row of lockers or something. Something like that. And two, let's add another space there, and let's just make a few of these. Yeah, that's good. So memory is like this, basically, and each memory location has some kind of address. Actually, let's be more creative. Let's start numbering at 12, why not? Like that, pretty much. And then each memory location can have some sort of value in it. So maybe it's 0 and the computer starts up, and then maybe you start doing stuff. Putting stuff in that memory. Like this. So memory's got a address and contents. And that's how the whole picture of memory in the computer works generally. So if you're In the C programming language, at least, you generally think of, now just to keep it simple, two types of memory. Now, it's not quite that simple, but generally you have a stack, statically allocated memory, and dynamic memory. So a stack is normally used for temporary storage of small values, stuff that's not going to live around for a long time. Dynamic memories heap is used for the opposite of that, so large values, big arrays of values, stuff that you need for a long time during a running program. Also stuff that you maybe know you need, maybe you don't need, know the size of what you're using, like you need memory for some purpose, but you don't know how much. A heap is good for that kind of thing. And a stack is kind of like, I don't know, a stack of pancakes. Yeah. Like that. And it's got a top and a bottom, so actually, why did it do that? Let's do it like this. Use hyphens instead. So you got the top of the stack, which has some kind of address. Let's say that. And then you got the bottom of the stack. Well, I can't count backwards in hexadecimal that well, so we're going to do it like this. And then so on. So a stack usually looks something like this, where this is the first value that you put on it, and it goes down, and its address is in memory. And the first thing you put on it is usually the last thing you take off. So if I put 2 on the stack, now 2's on the stack, and the stack pointer points to that location. Stack pointer always points to the value that was most recently pushed on the stack. So I got this big stack available. So I put stuff there. There's a 2, I put a 3 here. Now the stack pointer moves down. Now it's pointing to the 3 instead of the 2. And I put 4, 8, 9. Just making up stuff. Making up stuff you might put on the stack, any kind of number. Now stack pointer is pointing here, FFFB. So I got 5 values on the stack. If I take one off, I take the 9 off, and the stack pointer now points to 8. Now there's 4 values on the stack. And that's essentially how the stack works. If I take them all off, then the stack pointer points to memory right above the stack. And there's nothing on the stack. 0 items on the stack. So that's it. That's how the stack works. So you can put whatever you want in the stack generally, but it's not that big, and it's shared. So a lot of things might be used in the stack. So it's easy to run out of stack space in general. Where's the stack located in RAM? So in x86 assembly, you have control over the stack pointer. So let me move this. I'm deciding where I want to put this. Okay, let's look at the bootloader over here. So the 6502, you've got the stack in a reserved area, right? You can't move it, at least not the hardware stack pointer. I know you can have, there are ways you can implement more than one stack in 6502, but you got a hardware stack pointer, you can't move it around. Besides within the range that it's intended to move that one page, right? On x86, you can put the stack pointer anywhere you want to, as far as I know. So the conventional way to do it, and where it is here, is we put it at memory location 0. So when you push the first value on, that value goes into FFFF, since these are 64K segments. So that's what this is doing. XOR AXAX puts 0 into the AX register, and that's stored into all the segment registers, describing the current memory segment, including the stack segment and the stack pointer. So in our data model here, it's generally code. It goes into the lower part of memory, and then data, and then heap reservation, and then whatever's left is the stack, right above the heap. Now that causes problems whenever there's a problem with memory, either the stack or the heap. They tend to cause problems with each other, which can be kind of hard to figure out. Heap grows into the stack, or the stack grows into the heap. And I've implemented some checks, protection, to make sure that that doesn't happen, or we know when that happens. But it's not perfect yet. If you're in a CPU with memory protection, then you can reserve segments, and the CPU will generate a fault in these situations, which would be nice, but we don't have that in real mode, so we work with what we got. Don't cross the stack and the heap streams. All right, so that's a stack. So what's a heap then? Well, the heap is just this large. All right, so we could rearrange the stack, and actually it would look like this. And in fact, let's just do that. Hang on, let me make room for this down here. Copy all these and then put them next to each other. Nine 98432. All right, so yeah, just at this point, just imagine those boxes are up there up top. I might as well add them, gone this far, but I'm not gonna. Yeah, so again, we're just looking at memory. We've got sequentially increasing addresses and then the contents of the addresses. So this is the stack and that kind of representation. So top of the stack here, excuse me, bottom of the stack, first value in the stack. And then stack pointer points to the top. So in this case, stack pointer is pointing to FFFC there. SP. So the heap is also memory, but it's a lot larger. So your heap may go from, I don't know, let's say heap starts at A000 and goes to C000. So stack is like a few hundred bytes maybe. Heap could be kilobytes or more. So in this case, right, 1000 is 4096 bytes. I hope. So we're looking at a 4 kilobyte heap here. So it's a lot of memory. So if you need something big, a large file, graphics, stuff like that, your stack is probably too small. And it's not really intended for that, since if you leave the function that you're in C, your stack gets deallocated. So we use the heap for that kind of thing. And the heap is generally just reservations of memory. So I'm thinking about how to visualize this, how to represent it with my funny ASCII drawings here. Okay, so let's say that we've got a heap that we reserve. From A0 to D0. Yo. DFFF. Okay, so that's a 4K, right? No, each of this is 4K, so 16K. Yeah. Alright, so let's say we got a heap this big. And the way you use the heap is just ask for memory. So again, here we're initializing the memory here. Init. And then whenever you want memory, you can ask for it with the malloc for allocate function. So I don't know, where's that used? For example. Strings are probably a good example. Yeah, a good example, I'd say. So this function allocates a string being any sequence of characters of any length. So, hello, that's a string. Goodbye, that's another string. They're not the same size. So if you're a program, you might not know how long a string is that you need to allocate. Say, like if somebody typed it in, you wouldn't know until it came what size you needed it. So it's a good application for heap space. If a contrived example. So if you want something with a heap, you call this malloc function. Size of struct is the size of the memory, and then the size of the data in the memory. So we're getting stuff from the heap that way. And that goes to a heap allocator that I wrote. By the way, like all the code in this, not 100% of it, but almost all of it is stuff that I did. No C standard library from any compiler vendor or anything like that. Although I took a lot of help and inspiration from existing code. Definitely read a lot of existing code. Not something I recommend, by the way. And possibly not something I'd do if I started over. But anyway, the malloc function, you tell it what size you want, and then it gives you a block of memory, gives you a pointer to a block of memory. So if our heap is 16K like this, say that we've got nothing in the heap. Learning experience, yeah. For sure. So the heap, the allocator generally tracks free zones and reserved zones. So when you first initialize your heap, you've just got one big free zone. That's the entire size of the heap. So we said that we'd create a single heap. Sorry, we said that we'd create a 16K heap. So then we end up with a one free zone that covers that range. And we don't have any used zones. So then we come in here and we malloc space for this hello string. So after that, here, let me somehow keep track of what I'm doing here. We're going to malloc 5 bytes, and that's our hello string. Then after that, we've got one reservation, one used zone. And that zone goes from A000 to A004, 5 bytes. And then we have, I'm going to set that timeout to longer actually. Let's set that to 2 seconds. Okay, so we got one used zone, 5 bytes, and then our free zone is now A005 to GFFF. That's 16K minus 5 bytes. So then we come in here and do the same thing again. We allocate memory for another string, 7 bytes. And now our situation is going to look like this, where we've got another reservation. I know, I love the demo graphics. like that. Now AOC to GFF. So after allocating the second string, we've got two used zones. One 5 byte, one 7 bytes. They're right next to each other, right? So when one ends, the other begins. And then one free zone. And the size of the free zone is just the total heap size minus the size of the used zones. So you can see it starts at AOO, ends at DFF. And the only difference here being the size of the zones, what's used and what's free. So that's heap allocation. In C++, what did you use for rendering, do you remember? I really tried when I was in middle school and high school, and I always tried, but I would find tutorials on assembly on the internet and stuff, and I just couldn't get like from beginning to end. Like I couldn't find an assembler that would work, or it would be using a syntax I didn't recognize. I didn't have the manual for it, that kind of thing. Plus, the tutorials would sort of assume you knew what you were doing with assembly, and I didn't, so I was just never able to really get stuff done at the time. I guess I picked up something, though. It was helpful for later. Mode 13 VGA, nice. This is in DOS then, huh? What compiler are we using? DJ GPP or something? iDrive? Oh, Borland's nice. I tried, I was never... Till we had, till I could get books. I had the modern internet and stuff. Wasn't able to get the low-level stuff done. Now the information is better to come by for sure. It's still hard. In some ways. In other ways, it's not hard. Like what you learn this year is not gonna change out from underneath you in 1 year. And that's what I like about low-level programming. So we got 2 items on the heap here. So when the allocator makes these reservations, it sends the beginning address back to the caller. So if you reserved this memory for these strings, your first call would have sent this address back, AOO. Second call would have sent this address back. So you know where to write. Now you can use this memory for whatever you want. So that's how you reserve stuff on the heap. Then when you're done, you can free it. And you do that by calling them free. And just tell it what you're freeing, what the address is. So then you'd say free AOO. That's this memory that we allocated earlier. And then after that, you've got this situation. So the 7-byte reservation we didn't free, so that's still in the used list. We freed A000, so that's in the free list, but so is the OOC to DFFF. They're both in the free list now. They're fragmented, meaning that not all the free space is contiguous. Like one ends at one memory location and begins at one location and ends at another. So then if we free the second reservation, then you end up with this situation. Like that. About 5. That's what we meant to free. Okay, so now you've got this situation. So again, we don't have contiguous free memory. We've reserved 5 bytes, then we reserved 7 bytes, and we freed those 2. So we gave it all back. So the amount of free memory is the same as when we started. It's a whole heap size of 16K. But they're still zoned. So you've got 3 zones. And the heap allocator goes and consolidates those zones, puts them together, so you end up with what you... let's just put this here, internal consolidation of zones. Then you end up with the heap like you started with. So that's what the heap's for. So we talk about the stack and the heap. The stack is simple, you just put values on it and then pull them off when you're done. The heap is more complicated. You have all this zoning business. You have to keep track of the locations that you've freed and reserved. And you got to consolidate those zones. So there's a cost to that. It's slower, for one thing. If you don't keep track correctly of the memory that you've reserved, then it's easy to forget to free it or write over it when you don't intend to get corrupted memory and things like that. But definitely you want the heap. So that's a whole stack heap story. So that's what I was fixing. So the heap allocator, I wasn't properly checking the initial reservation size, which is this, the 16K. So when you're in your user program getting started, initializing the memory, you can tell it how much you want. And the way that works is actually in the executable file, which I guess we can go ahead and look at that in a second here. But it's stored there. When you create the executable file, the compiler puts that into the header of the file. And then we start to load the file. It looks there and finds out how much memory you want for the heap. And then the heap allocator gets that value. So I wasn't correctly checking to make sure that that value is actually available. And we end up with a bad heap to start with and memory corruption. So I fixed this bug. Now we just check and make sure, and we return a bad status code, an invalid status code. So if this happens, then we basically freeze the system with this assertion, assert false, and we print a message. So that looks good. I'll commit that change tomorrow when I have full attention to review it a little more carefully. So give me a second here. I'm going to take a quick break, and then I guess I'll probably talk about the executable file format since I kind of got on that topic. So I'll explain a little bit how my operating system kernel here loads and runs programs. So we have an executable file format called MKZ. So generally, what a executable file format is it's a program image. So it's a program that's ready to be run and has some information in the file that contains the image that tells the operating system how it can load the file and run the file. The OS usually needs that information. And these can be complex. If you've used DOS or Windows, you probably remember exe files. If you use DOS, you might remember COM files too. You would type the names in and run them. Windows still uses them, exe files anyway, but modern operating systems kind of hide those details as much as they can from users. But anyway, just think of, if you know what an exe file is, then you understand what I'm about to talk about here. And this one is really simple because of our memory model and the fact we just have a very primitive operating system right now. Stand by, I'm just going to think about how to explain this and refreshing my own memory. Alright, so I'm going to copy and paste this into a new window. So it's in the file format, these MKZ files that run the programs. Mostly it's just code. So if we write a C program for my operating system here, and then we compile it, we've got C object files, which are compiled to assembly. And the last step to create that MKZ file format is just to put some stuff at the beginning of the file. And we can just take a look at a small one. Let's look at the Hello World program. Oh, that's the text file. Where's the executable file? So, build. Hello MKZ. All right. Okay, so we're looking at like a 30 or 40K file, and most of this is the stuff that is compiled with, like system library stuff that I haven't separated out to make the file sizes smaller. But if we look at this, and I'll make the size a little larger here. So when we run this program, we get this hello world message. And you can see that string here that's actually in the file, and here are a bunch of strings related to like memory management and stuff like that. So all the code's right here. This MKZ file is mainly the program image to be executed. What's not is the first number of bytes here. So we've got, whoops. We got just a few bytes that tell the operating system how to load it. The first word of memory, a word being 2 bytes, a 16-bit value, that's a pointer into the main function, which is the program start function. So if we open up that program here, main, so in the C language generally, a program in C language will have a function called main, and that's where the program starts when you run it. And this is true here also, but the operating system needs to know where main is. You got to tell it that somehow. And sorry, got cat distracted. If you're using an executable format for a normal operating system, a supported operating system by your compiler, then it can just make that format for you. If you're writing your own operating system, you either need to support one of those formats or make your own. And in this case, to start, I decided to make my own. Although I may add support for exe or something else. So this first word, these 2 bytes, sorry, double word, 4 bytes. A word is 2 bytes, a D word is 4 bytes. So, the first word here is the pointer to the program entry point. So it's the address that the main function will be in memory. And because this is little endian, what we're actually looking at is, I believe, that segment and offset. So when the kernel opens up this file and loads it into memory, it knows that the first 4 bytes of the file are going to tell it where to run, where to put the CPU's program counter to run it. And then the next 2 bytes are the address of the return to kernel instruction. So that's where this goes when you return here, when you exit the program. We go to the address of the return to kernel instruction, and that instruction transfers control back to the program, back to the kernel, because the program's ended. So that's those 2 bytes. Now the third field here, start a free memory after program image. That's related to what we were just talking about, because this is the address of the memory that's available for the heap and the stack memory. So that's x86 within the current segment. So when the file's built, that address gets put into it, because the compiler tells us where the program data ends. So we know where the free memory in the segment begins, and then we put it into the file there. We do that when we build the MKZ file, and then when the kernel opens it, it says, okay, where's that memory start thing? And then it reads that, and for the heap allocator initialization, it uses that to determine where to put the heap in memory. And the amount of heap requested is done in the make file, the file that describes how to make all the different programs. We specify allocation size. So allocation size also gets stored in the program. And with those 2 values, the start of free memory and then the requested allocation size, the heap allocator can properly reserve the heap in memory. And that's how that works. Hey Metal Machine, are you ever going to try a plasma effect again? Might be time for a reprise. Since we're on the Whirlwind tour right now, let's go ahead and look at interrupt handlers. I need to do diagrams for these. because they're complicated enough that I forget how they work and don't understand them, and then are at bugs. Let's look at keyboard first, I think, because I think that'll be the simplest. Yeah, keyboard. Okay, so when I was talking about the kernel initialization routine, I mentioned that we install a lot of interrupt handlers. One of those is for the keyboard. And I kind of glossed over the reasons for doing that. Generally, when you've got some event that you don't know when it's coming, or some event that comes periodically, you've got two methods by which you can get that event or wait for that event. And one would be to poll for it. So if you're to poll for it, you would go to the keyboard hardware every so many milliseconds, let's say. And you look in there and you'd see, is there a keystroke in the buffer? Is there a keystroke waiting to be read? And if there was, you do something with it. So that's polling. Just going every so often to see if there's something to do with something else. And polling's fine, but sometimes there's better ways to do things. A keyboard is a good example because you don't really have any idea how long is going to pass before somebody presses a key on a keyboard. It could be milliseconds, it could be hours if they're away from the computer. So if you're checking every few milliseconds for a keystroke when there's no one at the computer for days, or even ever, if the computer's a server without a keyboard on it, then that's wasting time. It's wasting resources, wasting CPU resources as you do that polling. And it may complicate your program logic in some situations. So an interrupt can be a good solution for that. That's the other method to get an event. So polling and then interrupts. So polling we just talked about. An interrupt is when whatever event happens interrupts your program and says, hey, this event has happened. It's like the opposite of polling. Because when we're polling, our program has to maintain logic to go and see if something happened. When we're interrupt driven, we don't have to do anything except handle the interrupt. So that's how we generally want our keyboard to work. We install an interrupt handler, and when we get an interrupt or keyboard event, we do something in the interrupt handler. So our kernel here installs the interrupt handler for interrupt 9, which on PC architecture we're using the keyboard interrupt. And when we say we install it, what we mean is we point the interrupt vector table, which is in the BIOS, the computer's early memory, part of the boot system. We point that at this routine here in keyboard. So this is C code. C language code, and this is assembly. In our kernel, all the interrupt handlers are written in assembly. You can write them in C in certain situations, but we are frequently having to do stuff that you can't do in C in our interrupt handlers. So far it's been easier to write a lot of it in assembly. So here's what we do in the interrupt handler. We check to see if we're already servicing an interrupt. Not compatible with this one. Then after we're done with that, we switch stacks, which I'll get into at a later time, probably in next stream or something, after I do a couple diagrams. So we switch to the kernel stack from whatever stack we're on, because we may be on any program, user program. And then here we get whatever's in the keyboard event. So we read from the keyboard port and see what data's in there. The keyboard port being something that the hardware, PC hardware gives us, provides to us. From there we call this keyboard event and call this is actually C code. So we call out of this interrupt handler into C code to handle the event, which basically means we save it and send it to the kernel. Then we finish handling the event. This is a sequence that we need to use to basically tell the keyboard that we handled it and can get another one, because otherwise it won't send us another one because it won't know that we handled it properly. It'll just wait. Keyboard won't give us anything else. And we're done. So we exit the interrupt handler at that point. So that's what an interrupt handler does, and an important part of it is it must not disrupt whatever's happening in your system already. So let's see. Let's look at our loop program. We were running this before. All this program does is print numbers in a loop forever. It never exits. Well, it exits if you send an argument with a maximum number, but for the purpose of this discussion, it never exits. We're just in a big loop forever, and this program never exits. So what if you get a keyboard event while this program's running? What if that interrupt happens? Well, interrupt, by its nature, immediately gets called, immediately takes CPU execution away from whatever's running. So this program depends on all the CPU registers to be in a certain way at any given time. Its memory stack to be in a certain state. If any of that gets disrupted, this program will probably crash. It'll stop working properly. It won't do what it's supposed to be doing. So the interrupt has to save everything that it's going to change. It's got to be stealth. It has to make sure that nothing it does leaves the system in any other way than whatever was interrupted expects it to be in. That's one of the challenging things about programming with them. So that's what an interrupt does fundamentally. And then we have a few of those that we use. They're all described in this file. One of them is single step. This interrupt is generated after every CPU instruction. So you can use this to trace the execution of the CPU. If you're using an emulator, you have a number of ways that you can do that. If you're on hardware no emulator, then you don't have that. But you still need to be able to trace CPU execution state. So the single step interrupt on original x86s is a way to do that. And we do have some code to handle this. I started to work on a debugger that uses these interrupts. That's not working right now. I haven't maintained it. But ideally we get back to that. Timer is the system timer. So the PC hardware generates interrupt 8. That's a system timer that happens every, if I'm recalling correctly, 54 or so milliseconds. We get this interrupt. And that's pretty important. If you're an operating system, you need timing for a few different things. First of all, if you want to know how long you've been running, or how long any sort of operation is taking, then you need a timer. If you want to keep a date and time, then you need a timer. So let's say, modern operating systems synchronize the time by different methods, but if you're on an early version of DOS, early computer, you set the time, and when you turn the computer off, it probably goes away, and you turn it back on, your time isn't set anymore. But while you're running, your date and time are accurate. So how does it do that? Because it has system timer interrupt that it knows is going to happen every some milliseconds. It just keeps track of what time it is based on that by adding the number of milliseconds of this timer interrupt to the total amount of time for the last one. Keep track of the time that way. If you set the time to 12 p.m. and every 54 milliseconds you're getting an interrupt, you store that time, you add 54 milliseconds every time the interrupt comes, and you can pretty reliably know when it's going to be 1 p.m. based on that. That's the idea. And that idea is important for so many things. So say that you want to do a clock, or let's say you want to print a message every 1 second. Well, how do you know how long a second is? With a timer, you can do that. Now, in our case, we also schedule task switching using the timer. So this is a multitasking operating system, so multiple programs can be running at the same time. And the kernel implements that by switching between them. So if there's 5 tasks running, and the kernel runs, then task 1, task 2, task 3, task 4, task 5, then back to task 1. Just in a circle. But it has to time that. So what it does is this timer, we're actually looking at how that works. This timer gets a timing event. If it's exceeded some number of milliseconds since the last switch from one process to another, then it does the process switch. And the whole routine is pretty complex because we have to store the CPU state of current process in memory so we can put it all back the way it's supposed to be before we go back to that process. however many switches later. And then after we're done doing all that, we save the process, switch the stacks over, which involves a lot of juggling of the CPU register values. And then finally, call the scheduler, which figures out what process gets the attention next. Process that's the target of the switch. That gets loaded. That process state gets loaded. And then we switch over to the new stacks and return from the interrupt. So the old process might get interrupted. So let's say these two let's look at this one. These are both looping programs. This program just prints the time, the uptime, time the system's been running over and over again. And that steadily increases. So let's just run it just to demonstrate. Console's running, press time. Type time, press enter. Here's the time program running. So when I press Alt-N, that switches to console 1. Type loop. Here's the loop program running. So this is the program we're looking at on the right editor window. If I press Alt-N again, it switches back to the first program. That's what we're running on the left code window. Switch back again, switch back again. So the programs aren't actually running at the same time. One will run for a while. Then the OS switches over to the other one. Then that'll run for a while, and then the OS switches back to the first one. And that's how this works, it is interrupt. So the one will be running. It gets interrupted. It doesn't know what happened. It has no idea that it's been interrupted. And then the timer interrupts, saves the execution state, calls the scheduler down here to ask what program's next. Sorry, I'm losing my place here. Eventually, the other program that we're looking at would be next. So then the OS loads that program's saved execution state and then returns to it. So you interrupt one program, then return to another program. Then interrupt that program, then return from the interrupt to a different program, if that makes sense. Yeah, it's pretty cool how it works. Mistress Masterpiece. Bookkeeping, lots of it. That is for sure. And it's unfortunately pretty brittle right now. I mean, this is one thing I'm trying to just get a lot better at through diagramming and planning and testing, fuzz testing. Because any kind of enhancement or change that I've done so far has been liable to break a lot of things. And there's just a lot of work in maintaining the stacks and the registers. Like there's a lot of assembly code involved there. It's hard to move around and hard to reorganize and stuff like that. So it's definitely a topic of active research for me on how to make it better. And you get a lot of issues here with concurrency. Like if you're running a program and it somehow gets interrupted and then the same program gets activated but in a different place, then you might have the same program running twice. And if it's not designed for that, then you have issues of memory corruption. That sort of things happen a couple of times with the kernel. But where I'm going with it, what I would like to be able to do is run old DOS programs with multitasking. Like be able to run DOS Tetris and then press Alt-N and move over to, like, I don't know, whatever old DOS game that I'm not thinking of right now. Yeah, switch between two DOS programs. Doom, yeah. Not on a XT class hardware. On a 386, yes. But right now you can't do anything like that because all the programs are restricted to 64K memory. So anything that uses extended memory, anything above the 1 megabyte boundary is kind of out of the question at the moment. There's a lot of old cool stuff that'll run in 64K though. Old assembly games and stuff. All right, let's take a quick look at 4th, and then I'm going to end for the evening. So I showed the shell. And all the shell is right now is it manages the consoles and it runs programs written in C. So right now you have to, outside of the operating system, write a C program and use a C compiler. Again, outside of the operating system, and then transfer that into a disk image and then load the OS. There's no way to really do anything, create anything new inside the OS itself. And there are potential ways around that. What we're using is the Open Wacom compiler tools. As far as I know, that's the only actively maintained 16-bit C compiler, or compiler that will generate code for 16-bit CPUs. GCC will not do that. 32-bit and up only. LLVM will not do that. And I don't know of any others. Wacom's the only one. So short of writing our own compiler, C compiler, which I'm not wanting to do right now, that would be too much of a distraction for too little payoff, I think, since we already have Wacom. Our options would be to make programs in languages other than C on the operating system, or to port OpenWatcom would be one option. And it's a possibility, but it's kind of a tall order. But until we do that, until we address the situation, there's no way to really create anything in the operating system. You're having to compile stuff outside of it and then copy that onto disks and then put those disks into your old computer and start it up. And that's all right for a lot of things, but I want some way to actually be able to create programs on the system itself, create new stuff on the OS. So I played around with a couple of ideas, and the current one that I'm trying to make work is a language called Forth. And Forth was invented in the 60s, I believe. Started in the early 60s or late 60s. And has grown and changed and developed from there. And Forth is a stack-based language, meaning it's oriented around the memory stack that we talked about earlier. So that's what we're looking at now. We're looking at the Forth interpreter as an alternative shell. So in that other shell, I said, we can only run programs. We can't do anything else except run precompiled programs, C programs or assembly language programs that we made on our host and transferred over. Well, the idea behind having Forth as a shell, or as the start of a shell, is that we can actually create stuff on our machine here inside our operating system, on our old XT running this thing. So when the Forth interpreter is running, we can type in stuff. I'm getting bitten here. Hey, you gotta wait. Yeah, relax. Talking to the cat. Don't be alarmed. Okay, so it's ready for input here. So with Forth, we put stuff on the stack. And the things we put on the stack can be values, like numbers or whatever else. Or they can be words. And words are things that perform some kind of action. So for example, let's type 2, 3, plus, press enter. Forth says okay. So what that did was put 2, 3, and 3 on the stack, then put the word plus on the stack and have that operate on the numbers 2 and 3. Now the result of that's on the stack. So we can type .s, we can see the contents of the stack that way. So there's one value on the stack, and that's 5. So we added 2 plus 3 there. We got 5. And now 5's on the stack. We can go farther. We can say 2 star. Enter. Press OK. Now if we print the contents of the stack again, 10. So 5 was on the stack. We put 2 on the stack and the star word. And it took those things off the stack and did a multiplication. Now we've got 10. 10's on the stack. So that's how Forth works. So that's one idea I have to be used for a shell for this operating system, is to use a Forth interpreter to do that. Let's see, this is broken in a lot of ways. There's a lot of things that are not going to work and potentially crash, but let's see what else we can do here. What might be interesting right now. Also, I haven't looked at this very very much lately. Alright, Mishras, have a good rest. I'll see you later. Thanks for coming in. Okay, so let's print some stuff. So we're going to type 45, emit, press enter. And it prints a minus. Why does it print a minus? Because a minus is the character code. Sorry, 45 is the value, the decimal value for a minus sign. Or 5 decimal 2D hex. So you can see kind of the, well, let me move this window out of the way here. You can see a little bit better some of the character values here. So for 2 emit, we get a star. For 1 emit, you get the parens. These numbers are different because it's decimal versus hexadecimal. How do we do a literal, hexadecimal literal? I forget. Does that work? Yeah, it does. Oh, no, it doesn't. Stand by. Well, let's just go into the assembly code and look. Oh, it is right. I was wrong. Yeah. Okay. Got it wrong. Okay, I'm gonna clear the stack. I rock it. OS hype. Just showing off the experimental programming language and interpreter. Okay, our stack's empty, so again, looking at this ASCII chart, just driving the point home. So character hex, character, the @ sign, it's 40 hex. So this should work. Put 40 on the stack, press emit, and we get the @ sign. Now we can do this more than once. We can go 40, 40, 40, 40, 40, emit, 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 and we get 5 @ signs. So we can already use this as a calculator. 2 times 3, that should be 6. Times 3, that should give us 18. Let's check. Yeah, 18. What else could we do? Let's try. Let's see if something like this works. We can make functions to do other things. So they're called words and forth. So let's make a new word called my word. And that word is going to just add 10. Add 10 to whatever's on the stack already. Pretty boring, but let's try it. So stack has 18 on it. Let's just ignore that. Let's put 25 on the stack. Then my word. Now look at the stack. So the 18 that was on there is still there. But the 25 that we put on there is gone because my word took it off and added 10. So what else can we do? We know that we're looking at our chart up there. X42, when we emit that, that's a capital B. X62 is a lowercase b. So if we add 2O to 42, we get 62, and that lowercase is a letter. And that's true for all these letters. So let's employ that. Let's see if this works. So let's see if we can write a word to print both capital and lowercase letters. How do we define characters? I don't remember. How's your day going, Rocket? Yeah, that's how we do it. Okay, so we can type in a letter and we can emit it. Oops. Oh, you're doing a garage sale? Always good to have some help with the house upkeep, huh? I'm doing well. I've been pretty excited. I'm glad you redeemed this because I've been planning to do them for a long time and haven't gotten to it. Finally getting started. Gotta get rid of some of the stuff, huh? That'll be a good garage sale. If you're having it. Most garage sales that I go to are not ones that I really... not ones that I was happy to go to. Yeah, that's been true in my experience. I just usually don't have the patience. But I was doing some reselling a few years ago. And the odds are where it was at. If I spent a whole morning, I would find stuff that I was interested in. Same with estate sales. Thrift stores are another story, at least around here. Well, the big ones, anyway. Like Goodwill, I think anything I would be interested in, really interested in for retro gaming or anything like that, I think that stuff goes straight to the website or somewhere else, almost always. But I do eventually, I don't do this very often now, but when I was doing it a lot more, I would find stuff, not gaming stuff usually, but other cool things, occasionally at Goodwills. We have some other chains around here like Savers. I'd be more likely to find gaming and other interesting things there than at Goodwills. Yeah, the small local ones, that's where it's really at. Okay, what else can we do here? We put a string on the stack and then print it? No, we can't. In fact, I crashed it. I wasn't sure if that would work or not. So we'll restart, kind of wrapping up here. So what do we figure out? We can put a lowercase character on the stack and then print it. And we know we can uppercase the character by subtracting 2O. So let's do that. Put the lowercase character on the stack. Put 2 on the stack. Subtract it. No, that's not what I expected. Oh yeah, it is. I was looking at decimal instead of hex. So let's try that again. So we're going to put the lowercase character on the stack. Subtract 2O. Now let's look at the stack in hex. So that 6-1 is the lowercase character. We subtracted 2O. Now we got that 4-1 on the stack. If we we emit, we get the uppercase character. So we can uppercase any character by subtracting 2O. So let's define a new word that does that. Say upper. So upper is going to do that operation we just did. Subtract 2O and then print. But in fact, let's make it, see if I can get this right. Let's make a copy of the lowercase character on the stack. We print it, that gets rid of 1. And then subtract 2O, and then print the other one. That's our word called upper. So now we define a word, our stack's empty. We'll put the lowercase character on the stack, lowercase a, and then upper it. Okay, so then it does what I asked it to. It prints a lowercase character, then prints the uppercase character. Let's do it with B. Do it with Z. So we're programming. So that's kind of my idea for a solution. The problem that I presented before is that we don't have an easy way to create things with the operating system right now without getting a C compiler onto it, which looks like a lot of work and doesn't fit in with the memory model very well. So the fourth interpreter may be a solution there. That may be our shell and our programming language. Hi, Challenger. Let me know if you have any questions. So this is a work in progress. Fourth interpreter is not working very well. Fourth is a hard language for me to learn. But it's the best lead I've got. I looked at a couple other things like Lisp, Scheme, and tried them. I wasn't crazy about what I created, but Fourth seems like a way forward, I think. Okay, yeah, I'm just trying to explain everything I'm doing in some level of detail for everyone. I don't assume that anyone watching has any programming experience. So we looked at a lot of stuff today. We'll probably do one of these at least once every couple of weeks, although I may target once a week now that we've got the ball rolling on this, and we'll just look at new stuff. Upcoming plans right now, I'm working on stability. It is very easy to crash this operating system in very many ways. And since 16-bit real mode x86 CPUs have no memory protection, all the modern means that are available to stop these things from happening aren't available to us, so we have to get creative. So really improving stability and then getting the fourth interpreter to a point that somebody who's not a embedded systems programmer can put this on a floppy disk and put it into a computer and load it up and start using it to look at files and to make little programs and run programs and do fun things. That's really the short-term goal for this. let's get out of here. Let's find a raid target. Take this party somewhere else. Stuff made here? I have not. Let me take a look at that real quick.
Isn't it great?
Making hardware, huh? Robotics? Very cool. I'm gonna have to check this out. Thanks for the suggestion, Challenger. So if you're interested in this sort of thing, then I will be doing some updates on Discord in between. And like I said, I think every week, if not every couple of weeks, we will be doing either these or the NES disassembly streams. So if you're interested in that sort of thing, I'll definitely keep an eye out, like Tuesday and Thursday. I'll target for doing this. Updates in the Discord for sure. So who are we going to raid? Let's find out. And Rocket, thank you for doing the redemption. The big channel point redemption for the OS development stream. I was going to do it case by case when people started redeeming them. You're the first one that did it. But I realized I should just be doing them some sort of cadence anyway, regardless of whether they get redeemed or not. So I really appreciate you. I'm looking for people to raid right now. Let's head over to ECW Gamer. It's been a while since I rated them. Nice. I appreciate you redeeming them here. Let's head over to ECW. It's been a while. I can't tell what he's doing right now. Donald Duck going quackers on PS2. That's esoteric. Thank you everybody for being here. Rocket, thank you again for redeeming. If you're interested, stay tuned. I'll be back with more of this going forward. And let's head over to ECW. I'll be back tomorrow. No Mega Man 3. We got the PB. I'm taking a day off to give the hands a rest. But we'll do some gaming tomorrow. Just haven't figured out what yet. Have a good one, everybody. Thanks for being here. I appreciate you. I'll see you later. Be back tomorrow.